उद्या काय? Okay, so let's start discussion for today's session. Stereochemistry of polymers. The arrangement of side groups, particularly represented with R, on the sp3 hybridized carbon chain is described by the term known as tacticity of a polymer. According to the tacticity, there are three major types of polymers. Polymers, which are termed as stereoregular, are again subdivided into two types known as isotactic polymers and symbiotic polymers. Whereas in the stereoirregular polymers, the R groups are arranged randomly and called as atactic polymers. So let's see these types one by one. First, in this picture, you can see the R groups are arranged on the same side of this polymeric backbone. So when we represent this polymeric chain in with the wedge and dash formula, one can see the methyl groups are coming towards you. These are represented with these bold lines. Okay. So such type of polymers are known as isotactic polymers, in which all the substituents here in this case the methyl groups are on the same side. This is an example of polypropylene. Next are symbiotic polymers. So symbiotic polymer example of polypropylene, here one can see the methyl groups are arranged alternatively on this polymeric backbone. The methyl groups which represented with the blue color are going back or away from this plane, whereas the methyl groups written with the red color are coming towards you. So this is how we represent the symbiotic polymer, where the substituents are arranged alternatively in a regular manner. So both of these type, isotactic and symbiotic, are known as stereoregular polymer because the arrangements are in a regular manner. They are either on the same side or they are alternatively arranged. Whereas in the third type, the substituents are randomly arranged, that is, in an irregular manner. And these types of polymers are termed as atactic polymer. Here in this example, again we are taking polypropylene, but you can see the methyl groups are arranged uh, randomly or in an irregular manner. Some methyl groups are going behind, some coming towards you, but there is not a pattern. Okay, we cannot observe a pattern. Okay? There is no such regularity. So such type of polymers are called as atactic polymers, where the substituents are randomly oriented. Now we are going to discuss how these stereoregular polymers are synthesized. For that, an important catalyst is used known as Ziegler-Natta catalyst. It is developed in 1953, particularly used for the polymerization of alkene monomers. Okay. So alkene and its derivatives can be polymerized using this Ziegler-Natta catalyst. What is it? It is a combination of organoaluminum compound and a Lewis acid. There are different types of Ziegler-Natta catalysts, but most commonly used Ziegler-Natta catalyst is diethyl aluminum chloride and titanium tetrachloride. So these two compounds together are used as a Ziegler-Natta catalyst. When they are used, the active catalyst is formed by the transfer of an ethyl group from diethyl aluminum chloride to titanium tetrachloride. The polymerization is a stereospecific process when we use Ziegler-Natta catalyst, or we can say stereospecific polymer is obtained, and that depend upon the reaction temperature. If we do the reaction with the normal temperature conditions, we're getting isotactic, and if we maintain the temperature, okay, if we lower the temperature doing the reaction in a controlled manner, okay, we can synthesize symbiotic polymer. So this is very important catalyst for the synthesis of stereoregular polymers. So now let's discuss the mechanism of polymerization, which involves Ziegler-Natta catalyst. So the formation of active Ziegler-Natta catalyst is shown here when we have this triethyl aluminium, which is reacted with this titanium tetrachloride, and a coordination complex is formed. And in this, we can see one of the ethyl group is transferred to this titanium tetrachloride. Okay. And now this is our active catalyst or catalyst surface. This is a potential coordination site, okay, for the alkene. Okay. This titanium, which can bond here, okay, to the alkene. Now, when we use this catalyst for the polymerization of ethylene, okay, we'll take one molecule of ethylene and it binds to this potential coordinate site of alkene with this D and P pi bond. You can see the new dotted line which represent the formation of the bond between this ethylene and this active complex. After that, the insertion of this ethylene takes place, and this ethylene is added into this chain. So here you can see this chain, which initially has this ethyl group CH3CH2, is now added with this CH2CH2. Similarly, the step number 2 and 3 is repeated many times, and the every time the C2H4 unit is go on adding to this polymeric chain. So this is how the addition polymer is formed, or we can say chain growth polymerization process takes place with the help of Ziegler-Natta catalyst. Next are additives to polymers. There are three main types of additives which are commonly used: plasticizers, stabilizers, and fillers. So we'll be discussing these three one by one. First, plasticizers. These are low molecular weight organic liquids added to the polymer to increase its flexibility. By the word itself, you can understand this increases the plasticity of a polymer, and that is useful to reduce the brittleness. Okay, so I can mold the polymer and I can reuse it with different uh, purposes. In most of the thermoplastic, plasticizer reduces the cohesive forces between the polymeric chain, and thus it helps in increasing the mobility of these polymeric chains about each other. So that we call as flexibility of a polymer. The efficiency of plasticizer use depend on the factors such as solubility, polarity, and density. There are certain common plasticizers used. Example, few dialkyl esters like dibutyl phthalate, dioctyl sebacet, or aryl inorganic esters also used, known as tricresyl phosphates. Next type of additives are stabilizers. By the word itself, you can understand these are used to stabilize a polymer. Either it may be a thermal stability or electrical stability for the mechanical purposes. So polymers may change color and gradually decompose with evolution of gases at high temperature. The stabilizers are chemical compounds which are used to stop these degradation of polymers due to high temperature or any acid alkali treatments or chemical treatments. If we consider an example of polyvinyl chloride, in short PVC, okay, we know that it is not thermally stable. If we expose it to the high temperature, okay, it get degraded and HCl gas is evaluated. So we need to add certain substance so that HCl will not escape, and even if it is, then it will be neutralized. So for that purpose, certain compounds, organic or inorganic or even organometallic compounds are added as a stabilizers. So examples are sodium carbonate, calcium oxide, organotin compounds. Vegetable soils are usually used as a stabilizers. The third type of additives are known as fillers. What are fillers? The inert materials added to increase the bulk of polymer. Now they don't have any specific role like your stabilizers or plasticizers, but they are required, okay, for certain purposes. They are added along with the stabilizers, colors, and blowing agents. They used to improve the physical strength of a polymer. For example, if we take bakelite resin, okay, then the fillers like asbestos powder or sawdust is added into that, so that the bakelite, okay, which is a brittle polymer, okay, and its physical strength can be increased by adding these fillers. Even during the fiber forming polymers, okay, the molten mass is taken and in which these fillers are added just before spinning the fiber so that it will have a good tensile strength. Few examples of fillers are mentioned here. The fillers like sawdust, asbestos powder, gypsum, pepper, etc. are used and which gives the required physical strength to the polymer. So these are the three additives to the polymers: plasticizers, stabilizers, and fillers.